Cool. All right, guys. Welcome back. It's nice, with every due date in this class, I notice we lose 1 or 2 people in the room. That's okay. If I've done my job by the end of the anyway. Right. So hopefully you guys have all turned in your project proposals. If you haven't, you need to come talk to me because it was due. And if you recall the course policy, you're really not supposed to be using late days for that, right? So there's that. In terms of deliverables, your next homework is out. Has anybody opened it? Just wow. So you've downloaded it but not opened it. There was a graduate student in my office today who had a successful experiment and there was an obvious next step, and then they went to sleep. And I was thinking how do you do that? Anyway, that's okay. You do you. Cool. So good. So at least you can download it, and hopefully at some point you guys will attempt the homework. Would be good too. Other than that, I think your project checkpoints are in. Not due for a while. I'm going to try and email you guys comments on your proposals in the coming week or so. You have an irresponsible, over-committed professor teaching your class, so I'll do my best, and we'll see what happens. If they don't all come at the same time, you shouldn't feel like you're somehow slighted. Chances are I will download them in whatever order this thing does, and in the slot between 2 and 4 in the morning, send some comments a few at a time. So that's just how it's going to go. Any questions about procedural stuff? Cool. All right. So let's continue talking about geodesics. So we're going to get to the end of that. If we end early today, that's okay. We won't go to the next topic. I think it's reasonable. Okay. So stepping back a little bit from last time, remember that our basic starting point is that the term geodesic refers to the shortest path between 2 points, where you've added a constraint, which is that your path must connect those points on, a surface or manifold. Yeah? And we saw that a lot of things that are all true for shortest paths in 3D actually lead to different definitions when you're talking about a surface, right? You could talk about a shortest path as the thing that minimizes arc length. That's probably the one that we're used to thinking about. But a different definition of shortest path might be, kind of variational in nature. I toss a string to UA and we both start tugging on it until I can't do that anymore. And that would be a different definition. And then the third one is I look at my toes and I start walking forward, and I look at I stepped in some mud and I look at the path that my shoes trace out. And all of these things give you straight lines in 3D, right? They all give you geodesics. But on surfaces, they all give you slightly different objects. Yep. At least certainly the first and the other two. Yeah. Okay, so of course, we only have one hammer in this class, which is taking derivatives of weird things with respect to other weird things. And so when we wanted to talk about geodesics, that's precisely what we did, right? So the first definition we made is slightly useless in the context of differential geometry. Of course, in the context of global geometry, is super handy, which is just that a geodesic is the shortest path between 2 points. But of course, if we think of locally minimizing arc length, right? Then the fact that I said use words like minimize means take derivatives, set it to 0, and that was sort of where we were headed last time. But we stopped in medias res, right? We're right in the middle of our story here. Yep. So if we recall, our formula for arc length is here. Hopefully we all agree on that by now. But the big challenge, which you guys have dealt with on your homework, we've dealt with in class before, is that this term is just annoying to differentiate, right? Taking derivative of absolute value is no fun at all. Yeah? And so we proved, or at least attempted to prove, and I got myself confused a little bit, but that's just kind of normal in this class, a lemma which linked arc length, which is this thing on the top, to a different quantity, which we called energy. Right? So if I have a parametrized curve gamma, then energy and arc length are related by this innocent 2 here. But even if you're a computer scientist and used to thinking about stuff, right? This is least squares. That thing is least absolute value, right? And least squares is just easier to deal with mathematically. Yeah. And roughly that was more or less the motivation mathematically for introducing the second quantity. Although of course this happened a few centuries before we really cared about, I don't know, L1 versus L2 in the computer science field. They didn't have computers for one. But in any event, to relate these two quantities, we proved this lemma here, which is really just a corollary of Cauchy-Schwarz. And what this lemma is saying is that it is always true that length squared, my apologies for missing the squared when we were doing some of the math there, but we did fix it, is upper bounded by a multiple of energy. Right? And so one question you could ask is what happens if I minimize energy instead of length? Yeah? And essentially you can say, well, certainly the thing that I get when I minimize will have length, lower bounded by the length of the shortest curve. Yeah, that's the inequality here. And in fact, thanks to the equality case that we proved, they have to be the same thing. Yeah? So when I minimize energy, what I get is a geodesic with an added feature, which is that it's parameterized not by arc length, but by a multiple. Okay, so that's our story so far. Does that make sense to everybody? And thankfully, even though your instructor stutters and gets himself very confused in front of a room full of students, I did double check the course notes and they agree with me. So if you need a nicely written out version of that story, it's there. Okay, fabulous. So we did all of this work essentially because, remember, we have this kind of picture in mind. We've done it many times in this class already, where we talk about a geometric object as minimizing some functional, right? Like a minimal surface minimizes surface area, or a straight line minimizes length, or whatever, right? Then we take this variational derivative, and it tells us two things, right? One thing, it tells us sort of a condition we can check on this thing for whether it's a minimizer or not. So it'd be kind of like, checking if the gradient of a function is 0 to see if you're at least kind of locally at a stationary point. But in addition to that, it gives you kind of a gradient direction, right? It tells you how to flow an object to increase or decrease that objective value. Yeah? Is it true that the gradient direction of L squared and E here, remember that gradient direction is kind of like a vector field all the way along a curve in this case? Do those have to be the same? No, these are not the same. But they're very closely linked to one another. They're kind of scales of each other, right? Because essentially, all I did was take the integrand and change an exponent here. Right? I haven't done anything like really geometric. Yeah? So there's a little bit of a sleight of hand that happens in the differential geometry kind of standard literature, which is that we take the first variation of E, but really when they talk about the first variation formula, that's what they're talking about. And in the back of our head, we kind of remember that if I minimize E, I'm really minimizing arc length, and that's the thing I really cared about. Yep. One thing you can do at home, if you want to double check that there's order in the universe, is take the first variation of L. You can do it, it's just nasty. And you'll see that our condition for being a geodesic will end up being the same. You just had to do more arithmetic to get there. Okay? All right, so again, our goal for now is, Magnus draws a curve on a donut, right? He has some very thin thing of whatever it is that people put on a donut. And we want to check if that curve was a geodesic or not, right? I want to check, compute the gradient and see if it's 0. Yeah? And that's going to give us some condition for kind of understanding locally what it means to be a shortest path, because that's no longer obvious for on this curved object. All right, so what are we going to do? We have this E thing. We want to minimize it, so we take the gradient and set it to 0. And let's do that now. Okay, so, right. So what's our usual picture here? So let's say that I have a bunch of curves, and so here's my donut. And remember our discussion from last time, I don't have to have non-trivial topology, like a hole here, to get a curve that's not just like a kind of straight line looking object. But certainly this makes it easier to draw the picture. Yeah, so let's say that I have 2 points on my donut, and now I draw a path between these two guys, and I want to know if it at least locally minimizes arc length. In other words, there's no way for me to perturb this curve and make it shorter. Yeah? Okay, fabulous. So, right, so one way to do that is to kind of say, well, let's say that weren't true, right? Then one thing that I could do is I could start perturbing my curve and coming up with a whole sequence of curves that connect this guy and are shorter, right? So in other words, I can make a whole sequence of curves that I'm going to call, maybe I'll call the curve that I really care about checking gamma 0. And if it were not a local minimizer, I could come up with a whole sequence of like gamma t. I'm going to redraw this picture without the donut because it's a little easier to draw, right? Just a bunch of curves like that that connect these things, and the length gets shorter and shorter and shorter. Yeah. Okay. So let's say that I were in that scenario. Yeah? Well, let's compute the energy of gamma t as a function of t. So here you should think of t like time, right? So like I throw Fernando my piece of string, we start pulling on the two ends and the curve's getting shorter, right? And so as time evolves, that curve as a curve is changing shape, right? Okay. So, and what I want to do is look at the energy as a function of time, because if I take the derivative in time of the energy and I'm at the shortest, the curve can't get any shorter, what will d over dt of the energy be? Leanne, what will it be? 0. Yeah, there's only like one right answer if I'm asking for a number in this class. Right. Okay, so yeah, so let's do that. Okay, so remember, just for fun, let's write our formula again. So it's our energy of gamma t. Right, and this is another one of those scenarios where E is like this crazy object that takes in a curve and gives you some number. But then the way I'm going to get around that is that really I'm thinking of a function of a single variable, which is t. It just happens to be that I input t, I make a curve, I compute its energy, and when you compose all of those things together, it's just a function from numbers to numbers. Right? And that's how we use calculus. That's our sneaky trick in this class. Yeah? So again, the energy here is 1/2 the integral from a to b of mod gamma prime. Oh, I've overloaded t, I'm sorry. That's okay, we'll put an s here. ds. Okay, my apologies, there's a t there, s here. Cool? It's the same, I keep making the same mistake in this class. Sorry. Okay, right. So now, what do we have to do? We have to take dE dt. Yeah? So let's do that. So, do I want to go ahead and do it all at once? Yeah, let's do that. So we have d over dt of this e value. And remember, we only really care about t equals 0, right? Because that's the curve we're trying to understand. So let's go ahead and plug in t equals 0. Okay? So we're going to use our favorite fact that you guys keep calling me out on for using sloppily, and I'm going to do it again, which is this integral is over s, and I'm differentiating in t. Yeah, so I'm going to pass that derivative into the inside. Okay? So what do I get? I get that this thing is equal to 1/2 the integral from a to b of mod of d over dt of the norm of gamma t prime of s evaluated at t equals 0 ds. Cool. So I just kind of took my expression from before and clicked it in. Yes. Oh, fabulous question. So A, B, and T have nothing to do with one another. So A and B are kind of like the endpoints of the curve, and then T is which of the curves you're choosing as it evolves over time. So I have a bunch of different curves, like, you know, UA and I are playing jump rope, the curve is moving around, but the endpoints are fixed. You know, so as Sebastian jumps around inside of it, what he cares about is the moving part, and not the fixed endpoints. This happens a lot in our research group. Yeah. Okay, any other questions? Okay. Fabulous. So everybody with me so far? I haven't managed to make a sign mistake yet? This might be the farthest into the lecture where that's the case. Okay. So remember, this is a vector. So the norm squared is really, this thing is just the dot product of itself, with itself, rather. Yeah, so at this point, we're pretty good at the product rule. And conveniently, I stuck a 1/2 out here. Yep. So this quantity is really what? It's the integral from a to b. So now you have to be a little bit careful because there's two different derivatives hiding here, right? So we're going to have d gamma sub t prime dt evaluated at s dot product with gamma t prime of s. Notice that there's two derivatives in this expression. This is standard notation, but I hate it, right? Because the prime refers to differentiating in s, and then there's also d over dt, so I'm kind of mixing two things here. Actually, I don't know if I hate it. I mean, somehow this is separating out, like this is spatial and this is temporal. Right, that's what's going on. Okay, fabulous. So we only have like 3 sledgehammers in this class. I have an integral. There's a derivative in one term. There's not a derivative in the other term. It's important, you know, you got to follow the kind of the toucan Sam approach here, right? You got to follow your nose. So what should we do next? Integrate by parts. Thank you. You've also learned that I'll make it painful if you don't just answer my question. Okay, fabulous. So you've got a derivative times not derivative, right? So the boundary term is going to look like what? We're going to have gamma t prime of s, well, dot product with itself. Oops, which I'm noticing is a mistake in the course notes. So somebody should remind me to fix that. Actually, is that right? Oh, you're right. I'm sorry. Yeah, absolutely. So thank you. I just made the mistake. I just talked to you for like 10 minutes about a mistake that you shouldn't make, and then I made it. Right. So the integration by parts is in the s variable, right? Which means that the thing that we're dealing with is the primes. My apologies. And what we're going to do is we're going to move this prime off of this guy and onto this one. Okay? So the boundary term is going to look like, yeah, thank you guys. Sorry about that. D gamma t dt dot product with this thing. Yeah. And then minus the integral from a to b of d gamma t dt of s dot product with gamma t double prime of s. Hopefully you guys are getting some intuition for like how integration by parts and Stokes' theorem and all these different things, like their role in life is just to like move derivatives from one term in a product to another. Okay? So remember that when we're playing jump rope, we're moving our curve around, right? We're interested in the geodesic between 2 points. The endpoints are actually fixed. Right? They're not moving in our first variation formula. Yeah? So let's interpret, and remember this is, by the way, at t equals 0, all of this stuff. Yeah. Okay. So what is d gamma t dt evaluated at this thing? It's like the velocity of the endpoint moving. Right? Because remember that d over dt is velocity in time, and here I'm just fixing the s to be a. So it's just like I'm sitting at the first endpoint, which is gamma of a, and I'm noticing how it moves in time. It's going to be 0. Good, we got 1 engaged student. That's all I can hope for. Okay. Yeah. So what we're left with is just the second term here. Okay. And now, so maybe we'll. Actually, no. There's no reason to rewrite it. Yeah. Just look. There it is. Okay. So let's bond with this formula spiritually for a minute. Okay, so what's going on here? So first of all, so remember that, here's my curve. Here's gamma 0 of A. That curve does whatever it does. Here's gamma 0 of B. Yeah? So first of all, what are the d over dt's? They kind of look like vectors, right? And so this would be like you're fixing s and you're differentiating in t. So in other words, you're kind of like sitting at like a point on this curve and you're seeing how it moves as the curve changes in time, right? You have those like little vectors that are moving along this. I'm drawing them as normal vectors, but they don't have to be. They're just motions. Yeah? Okay? What is this second derivative here in s? Yeah, it looks an awful lot like curvature. I've used the term s here, and I haven't really told you that it's parameterized by arc length. If you want it to be, that's actually okay here. But yeah, so this thing kind of looks like curvature. This thing kind of looks like how I'm taking my variation of the curve. And so I'm in pretty good shape. So we're going to make one additional observation, and then we're done with our lemma for now. First of all, remember that gamma is a curve on my surface. Yeah? So, and this is the velocity of a point then moving along the surface. So can this be an arbitrary vector in R3? No. No. Where does it have to be? In the tangent plane. There we go. Yeah. So this is really at the tangent of at whatever the point is of your surface. Yeah. So let's think about linear algebra for a minute. I know that we don't like to do that. Yeah. So let's say that here's a plane. Maybe that's the tangent plane. Maybe it's just a plane. Yeah. And I have a vector which is sitting in that plane. And I have another vector which is potentially sitting out of that plane. I don't know anything about that guy. Okay, so I've got one guy that's sitting in a lower dimensional space, and then I got another one that's sitting in the space that includes it, like the immersion. Here's a fun fact from linear algebra, which you probably remember, which is I can take the projection of this guy into the plane, right? There he is. Wow, did I actually manage to draw that in a reasonable way? And I claim that the dot product between these two guys is the same as the dot product between these two. This makes sense, right? Because the additional missing part is orthogonal to the plane. Dot product of orthogonal stuff is 0. So I can do something kind of sneaky, which is this object, well, this thing is a tangent to my surface, yeah? This thing can point anywhere. I haven't said anything about it. Remember that, like if I'm driving a car along a surface, the acceleration can point anywhere, yeah? So, but one thing I could do is I could take this vector and project it into the tangent plane of my surface, and nothing will change to the integrand here. Yeah? So in other words, I could replace this thing with a slightly different value. First of all, we're going to ignore this first term because it's 0. We get minus the integral from a to b of this guy. He's some tangent vector s evaluated at t equals 0. And now I can dot product this with the projection onto the tangent plane, t, I guess, at gamma of s of your surface, of this vector. And these two things are equal to one another, right? And that's just applying this fact from linear algebra. And that by the way, proves this fact on the board here. Okay? Well, now we're cooking. You guys see that? So remember when we talked about curvature of a curve on a surface, right? We sort of said that we got this curvature vector, like I have a curve, PBAL, along my surface. I can drive along it, and I'd look at the velocity and the acceleration. That could be the acceleration of my curve. I can decompose it into two pieces, right? There's a component in the tangent plane, and a component that's orthogonal to the surface. Trivia time, what are the names of those two things? The tangent plane piece is what curvature? Geodesic curvature, and the normal part is normal curvature, yeah. Okay, so right. What is this thing? This is a geodesic curvature, yeah? This is exciting. You see what we did? We took the first variation of arc length, and we, again, like the same damn thing keeps coming back, which is this value of curvature. And so in particular, there's a very simple corollary to this fact here. Oops, I've revealed that your instructor is lazy and was print screening from his notes and cut him off a little bit. But in any event, if I want to be a local minimizer of arc length, what is that saying? That's saying if I perturb my curve at all, right, this derivative should be 0. Right? An arbitrary perturbation is kind of encoded in this vector field here. So if I want the integrand to be 0, no matter what I put in that dot product there, what had better be true about the other term?
Geodesic curvature is 0.
Fabulous. Yeah, this thing had better be 0 for my curve if I want this integral to always be 0 no matter what variation I take. You guys see that? Does that logic make some sense? It's the same logic we just keep applying over and over again. Yeah? So that's the corollary here. It's saying that if a curve is a geodesic, then the projection of the second derivative is 0. Or in other words, as you say, the geodesic curvature of my curve is 0. Let's think in terms of our driving car analogy for a second. Right? So what is this saying about my driving car? Remember that if I'm a passenger in the car, there are many different sources where I can feel acceleration, right? Like, if Magnus is driving, maybe he hits the accelerator and I feel it in the direction of the curve. So how do we fix that problem? We parameterized by arc length. Said he's not allowed to do that. He's got to move with constant speed. But then the acceleration you can still feel, yeah? And there's still two different sources that are left over, right? One of them is by turning the steering wheel, right? I can draw circles along the plane. The plane has no curvature, but my curve does, right? That's the geodesic curvature. And then there's a second one, which is I hold my steering wheel straight, and I just floor it, and I move forward, and I still feel acceleration because I'm driving up and down on a hill, right? Now I have a complete picture. Do you see that? Isn't that neat? Right? So again, our pieces are jamming the accelerator, turning the steering wheel, driving over a hill, and that's all the things that can happen to get curvature, or acceleration rather. Okay, so what is this theorem telling me? In particular, if I'm driving along a geodesic, I guess with constant speed is kind of implicit here, what force do I feel? Can I turn the steering wheel? Yeah, it's just for driving over hills, right? And this makes sense, right? Because if you're driving along the shortest path, you probably won't have like a U-turn in your path. Yeah. So essentially, this theorem is extremely intuitive. All it's saying is that if I'm locally a shortest path, then I'm not turning the steering wheel while I drive. That's it. Yeah? And so that's really the perspective that I would encourage you guys to have for this kind of fancy looking equation. Whether if you take Riemannian geometry, this is still true, but the proof that we wrote down like totally doesn't work, right? This depended on knowing that our surface was sitting in 3D. So you have to be a little bit more sneaky about it. Yeah?
I just wanted to confirm on the previous slide, the top equation has proj t gamma and it doesn't have an m. That doesn't mean anything, right?
Oh, that means I made a typo.
Okay, cool.
Yeah. If you remind me, I'll fix it. But again, there are many typos in the course notes, and I know that, but nobody's emailing me. You shouldn't feel shy to correct your instructor. I'm used to it. I saw a hand. Yeah.
We say in the first proposition that we assume you have a parameter s and t equals 0. But where is it using the proof?
It wasn't. So the reason why, you're right, I should rephrase this a little bit. The proof was just a variation, right? You didn't really need it. But if you want to think about this thing as curvature, then you do. Yeah, you're right. It wasn't really necessary. In fact, you really shouldn't have it because I put a and b there, and implicitly there's an assumption then the length of your curve is b minus a. Yeah, I'll rephrase it. It's a good point. Any other things I did wrong? Right. So again, the intuition here is very straightforward. You're driving along a curve, and the only acceleration you can feel is because you drove over a hill. Yep. Now there are many different ways to interpret this formula here. Right. One thing, the story that I told was, you give me a curve and I want to check if it locally minimizes arc length. Right. One thing I can do is plug into this formula and just check that I get 0. By the way, does that tell me it's the shortest path between 2 points? No, right? It could be, like for instance, on this donut, it might be that I had to drive all the way around the other side to get the shortest path. Yeah? That it doesn't know. But it does tell you that I can't like slip it along the donut a little bit and get it shorter. Yeah. So it is, oh gosh, I always get this wrong. Necessary but not sufficient. Yeah? Okay. But now, yet another sleight of hand happens in differential geometry when you read the treatment. In fact, sometimes there's some disagreement about like what's a definition and what's a corollary. All these things are equivalent stories. So what did we do? We started by saying, assume that I locally minimize arc length, then my curve satisfies this thing, right? But notice that this is just like think of, so gamma is effectively my unknown in this problem, right? It's my shortest path. So there's actually sort of two ways to look at this formula, which both appear in the geometry literature and go back to the introduction we had today. And they're mentioned here. Right? One is a boundary value problem, where I'm given 2 points and I want to find the shortest path between them, right? And in effect, what this formula allows you to do is maybe not find the globally shortest path, but like give you a gradient direction. So like, I guess given gamma of 0, gamma of 1, and a path connecting them, this gives you some machinery for being that guy that stands at the end and tugs the string until you can't do that anymore, right? But then, if you keep reading along in your differential geometry book, suddenly, like a weird thing happens, which is they stop talking about shortest paths and they start talking about other stuff like exponential maps. Yeah. And this is a thing that you're used to from differential equations class, but I think is another thing that kind of happens quickly sometimes in geometry and is worth noting a little bit, which is, if you view this thing as an equation, you can view it as an ordinary differential equation, right? This is some condition on a function gamma of s, right? And my unknown is gamma, right? And remember that, how many of you guys are taking some differential equations class? Just in 1D is fine. Yeah, so remember that there's like a lot of different ways to describe problems, right? Like, maybe I have some condition on the derivatives of a function and I specify the value at time 0 and the derivative at time 0 and I simulate forward. Right, this would be like f equals ma, I think is the example we usually think of. Right? And then if you took fancy physics class, you'll learn that there's like Lagrangian, Hamiltonian dynamics, all these other ways to describe that look something closer to a boundary value problem, right? Like the configuration at 2 points in time and you want to evolve, right? So we started with a boundary value problem. You could ask for a slightly different thing, which is an initial value problem, right? And what is this saying? This is saying I'm standing on a surface, I point my toes, and I start walking. And I want to walk in a way that locally traces out a shortest path. How do I do it? Well, one thing to do is to view this thing as an equation that I have to solve and solve it for gamma of s given gamma of 0 and gamma prime of 0. You guys see that? So I just kind of turned it into a definition rather than sort of a corollary. Yeah, and this happens quickly in differential geometry books, but it really is kind of an interesting point that like we're just taking this equation and interpreting it a different way, right? And this makes a lot of sense, right? This would be like, you know, Leanne has a soccer ball, she gives it a kick, and you just want to know where it goes, assuming it moves along a straight line, yeah? In, I guess, a gravity-free world. Right, so this picture of the world is useful for different applications, right? Certainly in physics and sometimes other places. And it leads to a very different object called the exponential map. Here's an example of the exponential map of the Earth from the North Pole. And the idea here is that if I choose a point somewhere on a 3D surface, right, for every point and tangent vector pair, there's a path that goes out that point with that initial tangent vector and so it starts tracing out a geodesic. Yeah? And so I can actually encode, well, if I have a geodesically complete object, I can encode the entire surface by saying for every point and tangent vector pair, I'm going to give as output to this function gamma v of 1. So in other words, a curve that's parameterized not by arc length, but kind of with velocity proportional to the length of v. Right? So in other words, if v is longer, I go faster, and I go for 1 unit of time. So in other words, it's kind of like I point my toes here, the length of v tells me how far to walk, and then I stop. Right? So this is a function from the tangent plane into the surface, which parameterizes it. Right? In fact, this is totally reasonable parameterization for a 3D object. This should also help you think a little bit about why geodesic distances are so confusing. In particular, let's say that I actually do this example. So here's a sphere. Here's a point on the sphere. Yeah. Oh, I forgot the obligatory thing that makes spheres, which is this weird curve that sits around it. Yeah. And now, what does the exponential map do? It attaches a little tangent plane at this point, right? And it maps tangent vectors to curves which kind of trace along it, and the endpoint of this curve is kind of the length of this vector. I've done a bad job drawing that. Yep. So let's take this tangent plane and draw it a different way, right? Let's just draw it as a plane. Yep. So what is the image of this point? It's just the center point here. So if I look this way, does anybody know why it's exponential? I haven't really talked about exponentials here. I'll encourage you to look into Google for Lie groups if you're curious. Okay, right, so in any event, this map makes perfect sense. Does the reverse make sense? So think about the Earth. Let's say that I kick off a geodesic and I start walking. I get all the way to the bottom of the Earth. I keep going. I ended up back where I started. Yeah? And so somehow, I mean, this makes sense, right? I mean, the Earth is a sphere. I think most of us agree on that. Show of hands. Cool. But I know that appears to be in question these days. But what's not true is that this is bijective, right? Like in particular, I can start walking along this thing and looking at the image on the surface, right? And for a while, it's tracing out a curve, and it might double back on itself. It could be that I get over here, and that this point also maps to P. Yeah? And this is a really critical issue in differential geometry, right? Because in some sense, like think about a computer graphics person. This is a totally reasonable algorithm. If you wanted to parameterize the surface, right? Like if you wanted to store a texture map on a 3D thing, you could compute the exponential map, at least in some neighborhood of a point. That's a reasonable thing to do. Yeah? But then you got to figure out where to stop. Yeah? Because eventually it's not going to be injective anymore. Yeah? Right. So in effect, you can draw a little region around this point here and say that inside of this region, I don't double back on myself. These are all the points where sort of it's the first time I see them. Right? In other words, I draw a ray out of the origin, and for a long time that ray is seeing the different points. Then eventually maybe that ray has an image somewhere else that already was seen in that radius. Yep. So if I draw a bunch of concentric circles, there are a bunch of circles for which this map is bijective, and then at some point it's not anymore. Yeah? Anybody know what that maximal radius is called? The injectivity radius. Yeah, the mathematician in the room knows. Yeah. Okay, so what does that correspond to geometrically? It's actually a perfectly nice picture. So let's say that I have, the injectivity radius. I mean, like, what is evidence for that radius? It would be like a point which has some other point where they both have the same target in the exponential map. What's the picture that I should draw here? What is this point?
South Pole.
Yeah, it's the other pole. And why is that? This point is equidistant to this one along two different geodesic paths. Yeah? And so that's the picture to draw here. And that's actually kind of, from a computer science perspective, a little bit scary if you think about it, right? Because there's an instability here, right? So here's a great example on the cone of the kinds of instabilities that can happen. So here are a bunch of different geodesics, and you can see that like sometimes they wrap around the surface, sometimes they do like a little loop. All of these things satisfy that ODE, but only one of them is the shortest path. Yeah. Instability meaning that if I start walking for a long time, the shortest path kind of looks like I don't want to use the word continuous because that's a weird thing here, but like I can like just keep extending shortest paths and they stay shortest paths. But then at some point I get over here, and if I extend it a little more, it's very hard for me to detect that actually there's a global change that needs to happen to this thing to keep it being shortest. Right? And the thing can snap around the surface. And this is a great example where it truly is unstable, right? Because if I take this point and perturb it a little bit to the left or the right or up or down or so on, the geodesic changes a ton, right? It rotates around the whole Earth. And this is a big issue computationally where we only have sort of approximate access to our surfaces anyway. Yeah? So oops, Lenovo hardware settings have detected a problem with your AC adapter. This fixed it last time. Okay. Oop, my screen just got dark. I don't know why it thinks that airplane mode will fix that. Okay. Right. So a different, yet another way to kind of talk about this is that if just because you locally minimize distance, like in other words, you take a geodesic and you extend it a little bit, then there's pretty high probability it'll stay a geodesic. That doesn't have to be true. Yeah? And that's a tricky thing. Incidentally, what that means is there's all kinds of neat structures that are hiding here. And for every one of them, there's some computer scientist out there that's thought of playing with this and applying it to a surface. So a great example is something called the cut locus. So the cut locus would be like I have some point, and now I look at the locus of all points for which there exists, say, two geodesics to the starting guy of the same length. Right? And so this forms some set of curves along my surface. So like the cut locus here is pretty boring. It's just an intibitable point, but that doesn't have to be the case. Yeah, this is an interesting set. And a different way of understanding it is that a cut point is a point where a geodesic ceases to be minimizing. Do you get why that's the same? Like I keep walking, and suddenly there was some ant that was walking another direction, and we walked into each other. That's what's going on. Yeah? Of a point. Yeah, exactly. So this thing depends on the source point. Absolutely. Yeah? Locus, the set of all stuff that has that property. It's just fancy math word. Yeah. Roughly. Okay. Right. So to conclude our discussion of theory of geodesic distances before we talk about algorithms, there's one other thing which is going to come a little bit out of left field, which is yet another way to describe geodesic distance functions. So far we've talked about geodesic paths, right? These are like a path from A to B, and you can kind of, you change the shape of the path and so on. That's a very Lagrangian view of the world. You guys know this distinction? I forget if we mentioned it in this class before or not. So there's kind of two ways to describe physics, right? There's Eulerian, Lagrangian. I think of like Euler and Lagrange as like somehow like frenemy kind of scenario. And so, right, so Eulerian physics would be like, let's say I'm describing fluid sloshing around in a tank. Then I would be like a barnacle sitting at some point in the tank and just like counting the number of molecules that move past, right? So this would be like I have a velocity field at every point, right? And the thing that's evolving over time is the velocity field. The other way to describe a fluid is Lagrangian, meaning there's a bunch of particles and I want to know like after 5 seconds, the particle that was here, where did he go? Right? These are two equivalent kind of pictures of the Earth. Right? So far we talked about kind of Lagrangian view of what it means to be a geodesic, right? We talked about curves and shortening the curve, and the curve is sliding along the surface, and it's a locus of points and all that good stuff. There's an Eulerian picture to be had here too, which is to talk about distance functions, right? So this would be like, I choose a point on a surface. There he is, yeah? And now I have a can of paint. I have many cans of paint that go from white to dark, yeah? And I want to just paint the entire surface in a way that gets darker as I move farther away from that center point. So in other words, I have a map from this thing into the real numbers. In fact, the positive real numbers. So it goes that way, which is just the distance to this point, right? And so this is some function on the surface, right? And you could ask for like what characterizes that thing as a function. So maybe I don't care about the curve, I care about the distance function. Yeah? And there's a really interesting, totally trivial observation about that function. Let's think about the plane for a second. So let's say I have a point on the plane. Let's call him P for short. What does my distance function look like? It's very simple, right? D of x we're not going to talk about other norms. Okay? What's the gradient of this thing? What's gradient of D? At this point, we've done this calculation more times than we can count, right? I'm going to get this backward. It's x minus p. Yep. Like that? Right, we've done some version of this many times already. So this thing is a vector. What can we say about this vector? It's pointing out. That's true. It's unit length. Yeah? By the way, it's also singular at x equals 0. Or x equals p, rather. But it's unit length. And why does that make sense? What is that? So in other words, this thing satisfies a condition, which is that it's length 1 everywhere, right? That's that triple equal sign. Why does that make sense? Roughly what this is saying is that distance changes at a rate of 1 unit per unit, which is true, right? If I move 1 foot, then distance changes by 1 foot. So there's like a 1-to-1 ratio there. Yeah? And that's what this expression is saying. Just trying to be careful about that. Okay, so we're going to do something funny. We're going to flip this equation on its head again and say, well, I could solve a really crazy nonlinear problem, which is to say, tell me what functions satisfy this condition, right? In other words, this is a differential equation. It's extremely nonlinear, right? This is a partial differential equation in D. And I could view the problem of computing a distance function as computing a D that satisfies this PDE. Does anybody know the name of this PDE? The IConnell equation. By the way, IConnell is not the name of a person. I always see it capitalized in papers. It is Greek for image, I believe. Image, yeah. Because it's, I don't know, image equation. Actually, I'm not sure why it's where that comes from, but that's the translation. Yeah. And so the IConnell equation is just this PDE that describes distance-like objects. And we're going to see that actually our algorithms, some of the algorithms that we'll derive for computing distances, you can view them as PDE solvers that are solving the IConnell equation. You have to be a little bit careful with this perspective on the world. This is extremely nonlinear. It looks innocent, but it's not. It's actually quite pernicious, this thing. In particular, I mean, there's a square root hiding in here, right? So there's derivatives underneath. Fine, you can square it, but you still have squared numbers with derivatives inside. This is no fun at all from a PDE perspective. Yeah? And in fact, there are many functions that satisfy this almost everywhere, which are pretty crazy, right? I mean, just in one dimension, right? Certainly, absolute value satisfies it, but so does like some stock market looking thing as long as the slope is always 1, right? So you have to be a little bit careful. Does anybody know what it's called when I just get the solution, which looks like shortest path to a single point? There's a special name for this kind of solution. This is advanced, there's no reason. It's called a viscosity solution to the PDE. I'll let you look up how that's defined. Okay, so that's the end of our math here. So now our goal is to compute geodesics on discrete things. Whew. Okay, and this is way easier. And that's because unlike many things we've already talked about in this class, like there really do exist shortest paths on polyhedral surfaces. And so we can just talk about them directly, at least to start, before we do some crazy approximations. Yeah? So the very simplest thing, so remember we have these different parallel stories for what it means to be geodesic. You could like solve that ODE, or you could tie a piece of string and tighten it, or you could compute the shortest path to some single source point. And of course, each one of those is going to have its own algorithm. So here's the simplest one, which is I'm standing at a point on a triangle mesh, I point my toes in some direction, I start walking. And I think all of you guys could write this piece of code. It's very simple, right? Obviously, when I'm in the interior of a triangle, what should I do? I'm not asking a trick question. Should move in a straight line, yeah. And when I hit the fold between two triangles, the kind of only reasonable thing to do would be unfold the two triangles into a plane, keep walking a little bit, and continue. Where do you think you would get stuck? Actually, with very high probability. You'll get stuck at the vertices of your mesh. And in fact, you can convince yourself that if you have hyperbolic and positive curvature parts of your surface, that this will happen more often than not. You'll hit right into a vertex, or at least kind of spiral into it. Right, so yeah, so anyway, this basic idea is this idea of a straightest geodesic. And it's kind of funny that we have to put a qualifier in front of the word geodesic, because we're used to thinking of them as being kind of unique. And we'll see why in a second. I really like these diagrams in this paper. They think of it like, kind of like, you know, putting in golf, right? There's like two flags and you're putting the ball from one to the other. Anyway, okay. So in this discretization, and now we're notice the word discretization is going to come up when we talk about geodesic curves. There's an interesting observation these guys make about geodesics, which is, remember discrete curvature? How we talked about it for a plane curve? Well, how could I check if a plane curve were a geodesic? Well, it has zero discrete curvature. Remember, we phrase that in terms of exterior angle. So one way to understand that is like, if I look on my left and I look on my right at any given time, there's 180 degrees worth of things, right? Whereas like if I made a discrete turn, there'd be like less on one side and more on the other. And so that's actually how they define a straightest geodesic on a polyhedral object. It's to say, I'm going to look at the sum of the angles on the two sides of any point on my curve, and when that sum is equal, notice I didn't say 360 degrees, then I'm going to call my curve a straightest geodesic. And at least for these two guys, it agrees with the notion of shortest path that we think it should. And there's only this one additional pernicious case, which is a curve that goes right through a vertex. We want to know, does that curve, is that thing a shortest path or not? I always vote yes. You guys are on to me now. Yeah, so it's not quite a shortest path. Yep. And so the intuition that you might have looks something like this, is that it's kind of unfolding, right? Like, so we've already talked about the case. We have two triangles that share an edge, and you can think of it like origami. You unfold them to the plane, and obviously a straight line there should kind of correspond to a geodesic on the folded object, right? Because that's really how you compute the length anyway. Yeah. But unfortunately, a kind of annoying thing happens when you're at a vertex is that you have Gaussian curvature. We already talked about this. Yeah. And what that means is that if you take all the angles that you sum up adjacent to that vertex, they don't sum up to 360 degrees anymore, right? In particular, if you're at a cone point, or at a positive curvature point, then they sum up to less than 360. Right? In other words, I take scissors, I cut it, like flat down on the plane, you're missing some angle, right? And if I'm at a hyperbolic point, then when I unfold it, like I cut one of the edges, it'll double up on itself. Hopefully this picture makes some sense now. Fabulous. So what is the straightest geodesic doing? Well, in some sense, it's just connecting stuff with a straight line, at least when you're not going through a vertex. The question is, what happens when you go through a vertex? Anybody have any theory? The really amazing thing is it actually depends on the curvature of the vertex whether or not this thing is the shortest path. And this is a really puzzling example. So in particular, the diagram that you should look at is here. So let's say that I have positive curvature. So in other words, when I cut, it kind of unzips. Yeah? And I have a curve that goes right through a vertex. Yeah? So there's this kind of degree of freedom, or like there's a thing to think about, which is I made a choice when I cut and laid this thing out on the plane. Right? Like let's draw this diagram so I don't have to wave my arms around. Right, so I've got two triangles like this. This is a weird way to draw it, but it worked out. and something like that. Yep. Okay. Right, and this corresponds to positive curvature if I glue these two edges together. Yeah. But notice that by drawing this picture, I made a decision, which is I made that particular cut. Right. I could have taken this triangle and put it here. Yeah. So there's some like kind of snipping and moving around that I can do when I draw this picture. Yeah? So let's say that I have a curve that goes right through a vertex, and he's got equal angle on both sides, right? Well, what does that correspond to? Well, for one, maybe I have a curve So the sum of the angles on the two sides at this point is going to be less than pi, right? Because I don't have as much to work with, yeah? So it'll kind of kink downward like that, maybe, yeah? Is this thing the shortest path? You can even see it right here. No, right? Because I could have just connected these two guys with a straight line and avoided that vertex altogether, yeah? Because remember, any way of unfolding this is valid, and if I draw a straight line, as long as the straight line doesn't hit a vertex, it's still a straight line when I fold this thing up, right? The length hasn't changed. Yeah? So in effect, what this ends up showing is that if you have positive curvature to a vertex, you can have a straightest geodesic. That makes perfect sense. You can ask for the angles to add up to the same number on both sides, but you can't call that a shortest path. And in fact, it's kind of an instability of length. It's like sitting at that vertex and it's not clear where to move, but any direction you move could potentially shorten it. Yeah? There are many options. Similarly, okay, so let's say I have a negative curvature, so it doubles up like that. Well, now notice there are many straight lines that go through that vertex, right? And in fact, all of these things have the same length, so the geodesic is non-unique, but there is a unique shortest, or rather straightest geodesic through that point. This is a kind of funny scenario where you make a definition that makes sense in the smooth case, and once again, it doesn't carry through, right? And in fact, there's a curvature dependence, which is really puzzling. If you guys are having trouble thinking about this, I encourage you to go home and cut out lots of sheets of paper and start drawing straight lines, and you'll very quickly get some intuition for what's going on. It's very hard to draw when you have a positive curvature point. This funny scenario on the left. Yeah. Okay. So anyway, that's the locally shortest picture is already kind of tricky. By the way, from a coding perspective, this is like no fun at all. This is actually something a little subtle. Like somehow this looks like the simplest thing. But think about what you need. Like you're walking along triangles, you've got to find the neighbors. There's like you need a full-on half-edge kind of data structure to do this efficiently. Yeah? Okay, so you could ask a different question, which is, okay, that was the locally shortest path, sort of, at least some definition. You could ask for what is the globally shortest path between 2 points. And in some sense, one good starting point is that we do understand algorithms for computing shortest paths on graphs very well. Although hopefully I convinced you guys in our last lecture that I can't just use those out of the box to compute shortest paths on a surface. Yeah? So the question is, can we make a little bit of an edit to these things and then use them? Yeah? And of course the answer is yes. Yeah? So despite graph theory people getting it all wrong, they have a few useful things to say, and we might as well highlight them. By the way, how many of us have heard of Dijkstra's algorithm for shortest path? Oh, fabulous. Okay. So remember what Dijkstra's algorithm does. You have a source vertex, and then you say, okay, what is the distance to the source vertex? Everybody? On 3, 1, 2, 3. 0. Thank you. Okay, so right, the distance to the source vertex is 0, and when I start my algorithm, the distance to everything else is, I don't know. Right? And I choose, so in other words, infinity. Yep. And then I say, okay, I have this priority queue of vertices, and I insert the source vertex into that priority queue. Right? And I sort it by distance. And I say, okay, I pull something out of the priority queue, so in this case, the distance 0 vertex. And I update the distance to all of his neighbors, right? So every neighbor, I say its distance is either the distance it already has, or the sum of the distance to the guy I'm currently considering plus the length of the edge to the next one, right? That's Dijkstra's algorithm. And then iterate, so then you throw that guy away, you add all the neighbors to the priority queue and continue, yeah? So if you think back to that algorithm, there are a few useful principles that it's really built on, right? One is that your shortest path had to come from somewhere other than the source point. Right, that's really what graph shortest path is telling you, right? That like every point has a predecessor in the shortest path, and that's the guy who came up last in the priority queue and updated you. Yeah, and that all pieces of a shortest path are optimal, right? In other words, if I have a vertex, I go from vertex 1 to vertex 2 to vertex 3 to vertex 4, and that's the shortest path, then the subpath vertex 1 to vertex 2 to vertex 3 is the shortest path from 1 to 3. That was a long sentence, but hopefully you all kind of parsed it, right? In other words, there's a kind of a recursive property going on. Okay. So let's start with Dijkstra's algorithm and think a little bit about what goes wrong, right? So let's put some notation here, right? So I have a graph. V0 is my source vertex. Di is my current estimate of the distance to vertex I. And S is the set of vertices with known optimal distance. In other words, I'd never have to touch it again. I know it's the length of the shortest path, right? Okay, so what does Dijkstra's algorithm do? Well, it essentially puts all of the things that you know are true, right? You certainly know that the shortest path to vertex 0 is 0, yeah? We're going to estimate the length of the shortest path to everything else to be infinity, but we're not going to have any confidence in it. That's what this is saying. And then, of course, you insert this guy into your priority queue, and that's what gets the whole darn thing started. Yep. So then, in iteration k, you look at the set of vertices that you don't know the distance to, but has the smallest distance. And you say, now I know the distance to that. Like, I'm just going to fix it at that value. This is a fancy way of saying that it's just the next closest thing that I haven't touched yet. Right? I'm going to add that to my set of things whose distances I know and update the neighbors. Okay, so does everybody see how this notation kind of aligns with the algorithm we talked about before? Fabulous. And then there's a very simple inductive proof that essentially says that in every iteration here, like certainly in iteration 0, S is optimal because it's empty, right? In other words, it's certainly true that in iteration 0, the set of distances that I'm confident in is empty. I didn't make any mistake, right? And then what this is saying is that I never add something to the set whose distance is not minimal. Right? That's a typical way to prove that this algorithm works, right? Because the set increases by one thing each time. Yeah, so it stops eventually. Okay. There's a picture that you can draw of what Dijkstra's algorithm is doing, which is kind of suggestive in the mathematical sense, which is, it has some center point. And if I just number off all the vertices, the order that they come up in that priority queue, right? One way to think about it is that I'm like kind of drawing concentric circles around the center point of bigger and bigger radius, right? And as that circle hits the next point, that's the next guy that I kind of pull out of my queue and update his neighbors. And then I never touch it again. Right? And so this key phrase that they use a lot in the fast marching literature. They call this the idea of advancing fronts. You have this front of vertices whose distance is known, but you haven't updated yet. And I'm going to keep kind of advancing it, like moving it outward. Right? There's some kind of militaristic picture to have in mind here. Okay? In other words, like Monde and I are sitting and our backs are facing each other and we're kind of walking out and taking care of the enemy line. Okay, so right, and so an example of Dijkstra's algorithm, which is quite simple, is maybe I start on the upper left. In their case, they've used 99 instead of infinity. Might I suggest in your code using int max? But in any event, in each case, essentially, the green set is the set S of things whose distance is known. It kind of expands outward. Notice it stays connected to. That picture makes some sense? Okay. So what we're going to do is we're going to talk about an algorithm called fast marching. This is actually an instance of fast marching. So fast marching is a generic technique for solving PDE, like the IConnell equation. But essentially, you can view it as a version of Dijkstra's algorithm that's modified to approximate geodesic distances. It's not going to compute them exactly. It's going to approximate them. This is sneaky. Okay? So the basic problem, the reason why Dijkstra's algorithm on a graph doesn't work is illustrated here, right? We've talked about this quite a bit, right? That the red edge length path is a pretty bad proxy for the green one. Yeah? So the basic picture of Dijkstra's algorithm no longer holds, right? However, this idea of advancing fronts still makes some sense, right? I can still have some queue of vertices that are kind of sitting on the outside and some approximation of kind of where the front is moving outward and kind of just keep pulling things out of the queue and updating their distances in a way that moves it farther. You know? That's what fast marching does. You know? But it does a really sneaky thing, which it says it's really hard to do that kind of bookkeeping exactly on a triangle mesh. Like I tried to draw it last time and I failed. But there's a simple observation you can make, which is, okay, right at the source point, the level sets of geodesic distance, they take all kinds of crazy shape. But pretty soon, as I move far out, they just look like straight lines. Right? They look pretty flat. That makes sense, right? Like if I have concentric circles, the bigger the circle is, the smaller the curvature. Yeah, that's all this is saying. And so what fast marching does, and it's an approximation of geodesic distance, it's not geodesic distance, is it approximates the moving front as a straight line. And that's the thing that it keeps advancing along the surface. But where do you think that the fast marching approximation is bad? Right close to the center point, right? Because that's where this thing doesn't really work. But we'll see one method that attempts to address that in a minute. Okay, so In other words, the advancing front really, by the way, should be a little piece of a circle, always on a triangle mesh, right? Like, because it's always just a bunch of planar things that are kind of going out. Yeah. There's like some probably beautiful optics picture that can illustrate this as it moves around a corner. But that aside, yeah, so it's going to make this approximation here, which is that your distance function just happens to take the form above, right? This is just the form of a linear function. Yeah? This is totally sneaky. Is this true? No. But it's kind of approximately true. And why does this help me? Well, in fast marching, what are we going to do to advance my front? I'm going to find triangles where I know the distance to two of the vertices. And when I know the distance to the two of the vertices, I can compute this vector n and this constant c. So in other words, I can kind of fit the distance function and then approximate the distance to the third guy, and that's how I advance the front. Sneaky, huh? And then what we're going to see is that because this thing is a hack, there's a lot of like cleanup we have to do afterward. Okay. There's one additional fact, which is secretly, of course, D satisfies the IConnell equation. Right? At least it would if it were a distance function. Yeah? It's a little bit of a lie, because this would be distance function to what? Well, nothing, right? It's a plane moving. Like there's no point here. There's no source point, rather. There's a point, which is computing distance. But in particular, okay, so the IConnell equation would say I take the gradient of this thing, and its norm has to be 1. So sort of a byproduct of that is that the norm of n here had better equal 1. Yeah? Sneaky, huh? So essentially I put a slightly false ansatz on the form of the distance function, and now I'm going to do a bunch of calculation on that because I know how to deal with that. Okay. Any questions about the setup? This little sleight of hand that happens? Okay. Fabulous. So let's do a tiny bit of math. So first of all, I can always take my problem and translate it into the plane, just for now. So to make my arithmetic easier, I'm going to assume that the point to which I do not know the distance is x3, and furthermore that that's at the origin. And I'm going to see that that's not going to matter in a minute. And the x1 and x2 are just in some arbitrary location. Yeah. So what are we given? We know the distance to x1 and x2. Notice, what does the initial step in Dijkstra's algorithm have to do? Well, the shortest path, you know the shortest path to at least 2 neighbors of the center point by those 2 shortest edges that come out. Yeah. Okay. So right. So we have d1 and d2. And we want to try to find d3, and because we put it at the origin, it's just this constant c. That's just it. Arithmetic makes your life a little easier. Okay, and effectively, what are we given? We're given x1 and x2, and our job is to find n and c. Yeah, that's what we don't know for our planar front. Okay, so I can write this in slick notation, right? So here, what's going on? So I define a matrix X, whose columns are x1 and x2. Right. So what is x transpose n? When our transpose rotates 90 degrees. So this is really like x1 dot product with n and x2 dot product with n, which is fancy notation for that. Yeah. And then that and this bold-faced 1 here is just the vector of all ones. Right, so this is just a sort of vectorized way of encoding these 2 relationships here. Does that make sense? Okay, great. So how many constraints do we have? How many unknowns do we have? So we're in the plane, really, right? Okay, so we have 1, 2 unknowns, because we're in the plane, plus 1 here. Yeah, so 3 unknowns total. How many relationships do we have? 2. So we're in trouble. What do we forget? What was that? Unit. The unit norm constraint. Yeah, we know one additional thing about our problem, which is that n has length 1. Yeah. Okay. Fabulous. So what do we know? We know that d equals x transpose n plus c times the vector of all ones, and we know that the norm of n is equal to 1. And this is a system of equations, so we can just solve it for n and c. Yeah? So let's do that. So this is a 2 by 2 matrix. Yeah, so I can just kind of invert it. Yeah? And of course, what I get is that, n x, the minus transpose times, I'm looking there, but this is obvious, right? Sorry. D minus C times the vector of all ones. Right? This is just by solving that relationship there. And now I can take this expression and plug it in here. Right? So in other words, I'm going to have 1 equals n dot product with n, right? Which is, of course, n transpose times n. Okay, so what is n transpose? It's D minus C times the vector of all ones, transpose x inverse x minus transpose D minus C. Okay? What isn't in this? Oh, that's why it's angry, because I keep stepping on my power thing. So, what's my unknown in this expression? How many unknowns are there now? There's 1. I eliminated n. I was sneaky. Yeah? Oops, I've pulled apart our whole system here. Man. Right, so there we go. And what is this relationship in C? Well, if I expand the square, I'm going to get C squared times some crazy constant plus C times some other crazy constant. In fact, I did it here. I don't think I'm going to write it, because why bother? Because at the end of the day, these are all just constants. Right? The only unknown in this expression is the variable C. Yeah? So what are we going to do after I get out of the way of the screen? This is a quadratic equation. Yeah? So it has 2 roots. Yeah? Negative b plus or minus square root of whatever. Yeah? And so what can I do? Well, remember that I was very sneaky. I chose to place my vertices in such a way that C is the distance I wanted anyway, and I've eliminated it down to 2 options. Yeah? So I'm in pretty good shape. Okay, so let's draw a picture of why I got 2 options instead of 1. And that has to do with this. So remember that n is a unit vector. What direction does n point? Remember we use the phrase like advancing fronts a lot? It's not just a unit length and normal to the front. It's the normal pointing out. Yeah? And so there's actually, that's the thing that we haven't figured out yet. And so actually geometrically this makes perfect sense. If I know the distance to 2 of my points and I'm trying to find the third based on a planar front, so there's like this ruler that's moving with constant speed along the plane and kind of hitting into my vertices one by one. There's sort of 2 different explanations I can get for 2 distance values. One is that it's advancing down, the other is that it's advancing up. And those correspond to those 2 roots C. Yeah? So here, let's see. What's the easier one to interpret? Yeah, so let's say that I know x1 and x2, and I don't know x3 in this picture. That's a slight relabeling from the previous slide, because I was lazy and I switched textbooks. Okay. Notice what happens in these 2 pictures. In one case, right, the front is advancing, actually let's start on the right-hand side. In one case, the front is advancing up. I guess it hits x1, and then it hits x2, and then it hits x3. In the other case, it's advancing down, and the opposite happens. Yeah? If I know, now let's think about Dijkstra's algorithm. If I know x1 and x2, what do I know about x3? It should be bigger, because that's my advancing fronts picture, right? Otherwise, I've violated the advancing fronts thing. So I actually have a rule for choosing between these 2 roots, which is just to take the bigger one. Cool. All right, so where does this go wrong? So, I mean, so many different approximations. There's no way that this should just work out beautifully. And the answer is absolutely it doesn't. In fact, right, so here you would choose the larger root, and I've conveniently drawn you a picture where this works. Where do you think you get in trouble? What do I do if I hit x1, x3, and then x2? Well, if I reverse it, it still doesn't hit. We purposely chose the larger one because I want to hit x3 last, right? But if I reverse the order, in that case, it still doesn't hit it last. Yeah? So in other words, I get in trouble. So the picture to have there is that this vector n is pointing in this funny way like that, right? So in other words, the advancing front, because I used this bad approximation, was actually explained by a vector outside of my triangle. And in that case, what happens? Notice that I hit x2, x3, and then x1. If I go this way, it's not going to change the fact that if this is my unknown, I've sort of violated my advancing front picture of the world. Yeah? What do you think fast marching does? A hack, that's what it does. It says, oh, well, that's a bad case, so let's not do that. So in that case, it throws out this computation and just uses, for example, the lengths of the edges and does like a step of Dijkstra's algorithm. Yeah? So that's the standard trick. If you're really good, you prove that actually converges. That's a tricky matter because you're sort of combining two algorithms. Yeah. Right. By the way, if you want a nice picture, you can actually check that there's like a nice linear algebra condition for checking when this is going to happen. And if we remember, maybe we'll put it on your homework. I noticed that the last 2 times I taught this class, I said that and I forgot. But yeah, so these are the basic pictures here. In one case, you can see the good one is the one where it really does hit x1, x2, and then x3. It's still an approximation, right? My fronts are still curvy, but at least it's kind of a reasonable one. And in this case, somehow, this advancing front picture and the planar front picture are at odds with one another. Yeah, right. And so there are many fixes. So the simplest one is to just resort to graph shortest path in that case, which is actually okay. I mean, the edges of the graph are distances. So at the end of the day, like it's not like you're doing something totally crazy, but you just shouldn't use that globally for the reasons we've already talked about. A different trick that people do is they notice that this crazy case can only happen when you have obtuse triangles. And so if you're careful, you can kind of subdivide your triangles in a way where you don't have obtuse triangles. And then run this algorithm and you'll just convince yourself this doesn't happen. That's okay, but of course then you got distances on a mesh that wasn't the one you started with, and so there's a little bit of cleanup you have to do. Yeah. Okay, right, so if we compare these two algorithms, there's a modified update step, where essentially now, instead of looking at all the vertices out of the next guy that comes out of the priority queue, you look at all the triangles adjacent to the next guy that comes out of the priority queue, and you use the planar front approximation to update them. Does that make sense? Other than that, Dijkstra's algorithm is the same. Yeah, so now you can all go home and compute your geodesic distances. And the kind of interesting thing, so this is the standard technique, and the two things to notice is this is not exact. This is not computing shortest paths on a mesh. This is solving a PDE. This is solving an IConnell equation using a linear approximation at every step. Yeah? And so it's kind of amazing that actually this is the state-of-the-art tool that most people use. So this is just a warning. So it's still an approximation, but it is a reasonable one. There are many ways that you can work on trying to fix this algorithm. One kind of well-known method is to say, well, I could take that planar front approximation and I could replace it with a circular front approximation. So that makes sense. Circles look like shortest paths. And indeed, that improves it. Apparently, this algorithm, my understanding in the kind of folklore is that this algorithm works well for short distances and the planar front works well for long distances. I wonder maybe there's some elegant way to combine the two. I've never really thought about it. And there's this used to be a cottage industry in numerical PDE. People came up with all kinds of cool IConnell equation solvers. I mean, you can also imagine these things are useful for solving a grid. And in fact, there are actually raster scan variants of this algorithm that take advantage of your graphics hardware to do shortest paths really quickly. If your shortest path happens to be the subset of a grid, there's some neat stuff you can do. And this is just the beginning of approximations of shortest paths on domains. So another popular one for something completely different that shows up a lot is leveraging, this is just a recent piece of research, leverages a connection between heat diffusion and shortest paths. First of all, we're going to come back to this later when we talk about Laplace operators. What is, you guys remember the heat equation, right? It says that like the first derivative of f in time looks like the second derivative in space, right? And this is the thing that we can solve on a surface. And there's actually a closed form on the plane for solving, right? It's Gaussian convolution. Yeah? So convolving against a Gaussian is kind of like taking a function, thinking of it like distribution of heat on a plate and diffusing for some period of time that I never get right. What is minus the log, square root of minus the log of a Gaussian distribution? Distance. Right? Remember that Gaussian distributions are e to the minus x squared, roughly. So if I do square root of minus the log, I get x, my absolute value. Yeah? But it turns out that relationship actually carries over to a curved object. And so there's a theorem by a gentleman named Verdun. Embarrassingly, I was recently, a couple years ago, giving a talk at NYU. I have a research paper that also makes use of that theorem. And I was talking about Verdun's theorem as a very classical result. It turned out that Verdun was in the audience, and I thought he was dead. That was unfortunate. But that aside, essentially what Verdin's theorem says is if you take the log of the heat kernel, then that thing for short time diffusion looks like distance. Yeah? And so in this heat method paper, what they do is they say, well, we know how to do heat equation. That's the thing we'll talk about later in this class. So we're going to postpone it a little bit. We're going to solve the heat equation a little bit, and then basically just take the log and call that thing distance. And that's a reasonable approximation. It's a little bit numerically unstable, so they have to do some tricks, right? They say, well, if I take the gradient of the log, that thing should satisfy the IConnell equation. It probably doesn't, so I'll normalize it and then kind of reconstruct a little bit. Does this thing satisfy the triangle inequality? Yeah, probably not, but it's efficient and it's easy to compute. And regardless if you do fast marching or any of these other techniques, it's actually quite easy to trace the geodesic curve by kind of working backward. So you have the geodesic function, you want the curve, you start from the target, and you just keep basically doing gradient descent until you end up back at the source. Yep. To spend just a few more minutes talking about some other methods so that we can wrap up geodesics. The obvious question here is that polyhedral surfaces are pieces of geometry, and you could ask for like the honest to goodness daggone shortest path on that thing instead of all these crazy magic tricks we're doing to get around that. And indeed, there is an algorithm. I encourage you guys to read it on your reading assignment in this class, so you can suffer like I did when I had to read this thing. This is a very famous algorithm by Mitchell, Mount, and Papadimitriou. And in like 10 seconds or less, the issue becomes the following. So let's say I have even just a triangulation on the plane, and I want the shortest path. By the way, when your triangulation is non-convex, that's actually equally annoying to a 3D surface. That turns out not to be the hard part. And so essentially what this algorithm does is it keeps track of these windows, where in this entire yellow window, if I kind of did that backward gradient descent pass, it would hit the same sequence of triangles. Do you see that? But notice that window ends in the middle of an edge. Yeah? And so this is a variant of Dijkstra's algorithm where what they have to do as they work outward is advance not the vertex distances, but they actually have to subdivide the edges as they do that and advance these windows going outward. That's kind of a reasonable thing to draw a picture of. It's like just a giant pain to look at the code, but more importantly, from a complexity theory standpoint, this is quite difficult to analyze, right? Because you have to bound things like how many times can any given edge get subdivided in a procedure like this. Because for all you know, this algorithm never terminates, right? Like maybe it keeps dividing every edge in two, and the geodesic path just keeps circling around, right? And so there's a lot of work you have to do to say much about this thing. Just recently, people have actually gone back to this algorithm, and there's a few papers that try to implement it, which is like kind of amazing. I encourage you guys to look this paper up at home and just see the amount of work that they have to do. This is like definitely falls in the computer science theory kind of world where it's like everybody acknowledges that it exists and nobody codes it up kind of things. But it is true that like the constant sitting in front of this algorithm isn't terrible, and if you really care about that shortest path, you can get it. Yep. To summarize in 4 minutes or less, some other interesting things you can do with geodesics, so that next time we can talk about inverse problems and finally do some machine learning. Remember we talked about cut loci? And for some computational problems, actually, especially in computer vision, this is a little problematic, right? Because like, you very rarely want things that are discontinuous or change very rapidly, depending on where you are on a surface, right? And so there's some question which is like, you know, if I care about the shortest path between 2 points, like think about robotic path planning, right? Maybe I want to know like all of the reasonable ways to get from A to B that are more or less the same length, that kind of thing, right? Right, and the cut locus being the big problem here, that like I could perturb a point slightly and the structure of the shortest path changes globally, right? This happens on graphs too, by the way. This isn't just surfaces. There are a few papers that try to address that. One of the kind of funny ones is this thing called fuzzy geodesics, where they define a function on the surface, just like geodesic distance function. Now we're going to have 2 points on a surface, and we're going to define the fuzzy geodesic function, which says I'm going to look at the length of the path from P to the point, and then the point to Q. Right? If that thing is on the shortest path, then the sum of those two things should be the geodesic distance. Right? And of course, that thing drops off the farther I am from a geodesic. Right? And so they define this thing to be sort of the sum minus the actual length. They take a Gaussian in that, and you get this nice function, boy here, which is kind of highlights the places where you could have placed a geodesic and done a reasonable job. So for certain shape analysis applications, this is kind of useful because it's like a stabilized version of geodesic. There's also, if you want a giant headache, some interesting techniques that consider the case of like maybe I have polygon soup. So I have some notion of tangent plane. I think I can do better than shortest path on a graph. But you know, some jerk has scanned this horse and like it's missing his midsection and the triangles are rotated in funny ways. And so there are these funny versions of Dijkstra's algorithm that try to do fast marching when it can. Like maybe every once in a while do a planar front step when there's a triangle that's kind of aligned with the front, and then you resort to something else when you can't. These are all, if you haven't noticed, our lectures kind of keep following the same structure, right? Like there's theory, a few algorithms we do in detail, and then a picture book of other stuff you could do. This falls into the picture book category. And then there's some other interesting techniques out there. So for instance, if I wanted all pairs distances, or like this kind of thing where I have a measuring tape and I'm going to keep holding up the measuring tape to different pairs of points on a surface, and I want to know if there's some pre-computation I could do to accelerate that. This shows up a lot, by the way, especially in logistics style stuff, right? Like I'm running UPS and the roadmap doesn't change all that much, and I have to route trucks every which way. So it might be worthwhile to spend some time analyzing the roadmap, and maybe knowing something about the distribution of supply and demand, and then doing a bunch of shortest paths all at once. So there are some interesting algorithms for this. They're largely kind of heuristic. It would be fun to reconsider this. This would be a great project for this course, by the way, because it's too late. Well, like, so for instance, what these folks do is they kind of take a network of points over the surface, and they build a graph and compute shortest paths there, and then kind of do this proxy thing where you kind of snap to the closest point, use that path, and then take another shortest path. So in other words, they only ever have to compute geodesics inside of these little triangles, and then they maybe like locally refine it a little bit. There's probably a universe in which you could prove something about this method. I don't think about it. I don't know. And there are all kinds of other tricks. Like, so for instance, how many of us are familiar with a Voronoi diagram? Cool. So Voronoi diagram is like you have a bunch of points on a domain, and then the Voronoi cell associated to a point is the set of all points which are closer to that one than any other. Yeah. And so geodesic Voronoi algorithms are useful. In fact, they give you a triangulation on the surface, which is pretty cool. But in order to do that, you kind of need lots of short geodesic distances, right? Dijkstra's algorithm is actually super useful for this because there's no reason why that set of points whose distance you initialize to 0 has to be one point, right? It could be all of the source points. And indeed, that's sort of the reasonable way to get a geodesic Voronoi diagram. And then something, unfortunately, in this class we won't have time to talk about, but is super fun, are geodesic problems in extremely high-dimensional spaces, which actually show up in applications. Some students were in my office the other day. We were talking about some of these things. So let's say I'm thinking about computer animation, and I have this hand in 2 different poses. These are points, believe it or not, in r to the 3v. In other words, I make a giant vector of all the vertex positions. Yeah? And that is a very high-dimensional space, and you can put a geometry on it that has to do with the elasticity of the surface. And then one of the interesting animation tools out there that's been largely explored, there's like a whole set of authors here that like keep reappearing, and so if you like this kind of stuff, you should look them up. That say, well, one way to do automatic computer animation is to compute geodesics and splines in this weird Riemannian manifold, and they have extremely impressive results. So to conclude, one additional paper to look at, which I think would be a fun one to do in your reading, is in the machine learning case. So it's sort of, there's a very common practice in machine learning, which is I want shortest paths between points, and I just have a big point cloud. So what I'm going to do is construct the k-nearest neighbor graph and use distances on that as a proxy for distance, and somehow that seems reasonable. In fact, like all of the counterexamples I gave you to graph shortest path were very carefully constructed, right? Like I drew all these triangles, and so there's a question like, on average, can that happen, or is that just like because I was evil and drew a particular structure? The answer is no, it's still not a good idea. So this research paper, essentially, they prove an unfortunate result, which is that for unweighted KNN graph, this distance converges to an unpleasant distance function. I really like that phrase. But what it doesn't converge to is geodesic distance, yeah? So later on we'll talk about heat kernels, and indeed what we'll see is that that's a place where you can say something about geodesic distance. So with that, I think we're done for today. Don't forget, I don't know, whatever your next deliverable is in this class, and I'll see you on Tuesday.